In the last video, we talked about inverse functions. And one thing that I want to wrap up before we start talking about exponential functions is the following. So, the graph of an inverse function can be found using kind of a neat trick. So we know that f of x is equal to y if and only if f inverse of y is equal to x, for a function f that actually has an inverse function. And so the point x comma y is going to be on the graph of f if and only if y comma x is on the graph of f inverse. So to show you what I mean by that, let's say this is a graph of f for some function f. Alright, so I have a point here at 0, comma, I don't know what this is, let's say 1. That means 0, 1 is on the graph of f if and only if 1, 0 is on the graph of f inverse. That means I'm guaranteed to have a point here at 1, comma 0, because when you swap the coordinates, you get a point on the inverse function. Similarly, let's say we had a point here at 1, comma 2. That means we'd have to have a point at 2, comma 1, 2, comma 1 for the inverse function, because we can swap the coordinates. Alright, and if, let's say, this here was point 2, comma 4 on the graph of f, that means we would have to have a point at 4, comma 2. Put it in blue, on the graph of f inverse. Okay, and so we end up getting this new function that looks roughly like this. Okay, so notice what this graph is. This is a result of reflecting the graph of f, that's our red line, over this diagonal line here. I haven't drawn it exactly perfectly. But if you take this diagonal line, and this is the line of y equals x, and you reflect your function across that line, you'll be left with the graph of f inverse function. Okay, so this is sort of a neat trick for sketching the inverse function of a graph if you know what the graph of f looks like. Now, this graph here, this red one, it leads us into what we're talking about in the next section, which is exponential functions and their graphs. So we say that the exponential function with base a, I spelled it wrong in my video, B-A-S-E, base a, is denoted f of x equals a to the x, where a is just some real number that's greater than 0 and that's not equal to 1. The reason why we say that it can't be equal to 1 is that if it was equal to 1, if it was just 1 to the x power, it wouldn't really be an interesting function to us, because no matter what you raise 1 to the power of, you're just always going to get 1. So this is really just a constant function. So we don't really consider the case where f of x equals a to the x has a base of 1, but we'll always assume that a is positive and that it's not equal to 1. Now, there's a big difference between an exponential function, like, for example, f of x equals 2 to the x, and a polynomial function, f of x equals x squared. So if I were to sketch this graph f of x equals 2 to the x, it would look something like this. Okay? It would grow very quickly in that first quadrant, and then in the second quadrant, as x heads to negative infinity, we get this horizontal asymptote at 0. F of x equals x squared, on the other hand, looks like this. Let me use a different color. Okay, it looks like a parabola. Now, you might be thinking to yourself that, okay, obviously it's different in the second quadrant over here, but in the first quadrant, they look a little bit similar. Don't be fooled, though, they are very much not the same, right? They grow at very roughly the same speed at first, but once you get to, say, let's say, f of 5 in the second graph, this would be 5 squared. That'll give you an output of 25. So we'd have a point way up here somewhere at 5, comma 25. Whereas in this first function, f of 5 would be 2 to the 5th power. Right? This time the exponent is variable, so it would be 2 to the 5th power, which means 2 times 2 times 2 times 2 times 2, which means 32. So we'd have a point here at 532. So at this point, my f of x function is going to be outpacing, right, or my 2 to the x function is going to be outpacing my x squared function, right? It's growing more quickly, and it's going to grow even more quickly the further we go on. So if we only went as far as, let's say, an input of 10, In the first case, f of 10 is equal to 2 to the 10th power, which is 1024. Whereas in my second graph, f of 10 would be 10 to the 2 power, which is just 100. So we can see that the blue graph, the exponential graph, is growing much, much, much quicker than the x squared graph, the polynomial graph. In general, exponential graphs grow much faster than any polynomial functions once you get to a large enough value of x. That's if the base is bigger than 1. So if not, we'll talk about that in a different example. But now let's try to compare some exponential functions to each other. So let's try to compare the graph of 2 to the x and 4 to the x. So I'm just going to do this by plotting a few points. Let me start with the f of x equals 2 to the x function. So if I'm going to plot some points here, let's say x is equal to negative 2, I'll get 2 to the negative 2 power, which of course just means 1 over 2 squared, which is 1/4. If I plug in negative 1, I'll get 2 to the negative 1 power, which is 1 over 2 to the 1, or 1/2. If I plug in 0, I'll get 2 to the 0 power. Anything to the 0 power is just equal to 1. I should be plotting these points as I go here. Negative 2, negative 1, 0, 1, 2, and 3. So I'm going to be plotting a point here at negative 2 comma negative 1/4. That's really close down here. At negative 1/2, it's a little further up. At 0 comma 1. Then when I plug in 1, I get 2 to the 1 power, which is just 2. So that's a point at 1 comma 2. If I plug in 2, I'll get 2 to the 2nd power, which is 4. So I'd have to plot 2 comma 4. And then if I plug in 3, I'll get 2 to the 3rd power, which is 8. Oh boy, 1, 2, 3, 4. So it's going to be all the way up here. All right, this is growing awfully fast. This graph is going to look something like this. Okay. I didn't draw this super well, but something like that, right? Similar to what we drew in the last page. Now, the g of x function, which is 4 to the x power, is going to be a little bit different because we'll have, let's see, g of negative 2 would be 4 to the negative 2 power, which is 1 over 4 squared, or 1 over 16. So this is even closer to the x-axis. All right, if I plug in negative 1, I'll get 4 to the negative 1 power, which is 1/4. Okay, so now I have a point here. If I plug in 0, I'll get 4 to the 0 power, which is just equal to 1. So, okay, they intersect here. If I plug in 1, I'll get 4 to the 1 power, which is 4. If I plug in 2, I'll get 4 squared, which is 16. Oh boy, I can't even draw that. It's way off the charts, right? Way up here somewhere, even higher than that probably. And 4 to the 3rd power is 16 times 4, which is 64. Oof, way, way, way off the chart. So if I were to try and draw this red graph, this 4 to the x function, notice that it grows to 0 more quickly than the green function does as x heads towards negative infinity, but it also heads towards infinity much more quickly than g of x does for positive x values. So the larger the base, the more quickly it will grow. More quickly it will grow towards infinity. All right, so let's think about what other graphs might look like for these exponential functions. So we've seen already that the general shape of a graph of the form f of x equals a to the x, where a is bigger than 1, like we saw a base of 2 to the x, or 4 to the x. The general shape was something like this. So it has a y-intercept at 1, because a to the 0 power is equal to 1, right? You always have a point 0, 1 there. And it's got a horizontal asymptote as x goes towards negative infinity at 0. Then it grows very quickly in the first quadrant. Now, f of x equals a to the negative x is the result of reflecting a to the x over an axis. Remember, think back to when we did our transformations of graphs. We said when you replace x with negative x, that has the same result as reflecting a graph over the x-axis. Okay, oh sorry, this is the y-axis. Reflecting a graph over the y-axis. And so the graph of a to the negative x is just going to be the same graph we had up above, but reflected over the y-axis. So when I reflect it over the y-axis, now it's growing really quickly in the second quadrant, and now in the first quadrant I'm going to be approaching 0. Okay, so this is what the graph of a to the negative x would look like if a is greater than 2. Now, a quick note, let's consider the graph f of x equals 2 to the x. We know it looks roughly like that red graph we drew up above because we've already drawn it a few times. What would the results, let's call this new graph, 2 to the negative x be? Well, remember, we could rewrite this as 1 over 2 to the positive x because a negative exponent is the same as moving it to the denominator and making that exponent positive. And we could rewrite this whole thing as 1/2 to the x power by pulling the x out in front. We can do that because we could, for example, put an x here and it's not going to change anything. Right? And so this is actually telling us the general shape of a graph for a function f of x equals a to the x, where the base, a, is less than 1. It's going to look exactly like this, right? So this red one is what the general shape of a graph is for a greater than 1. And this blue one is the general shape of a graph a to the x where your base a is less than 1. Just a good thing to keep in mind. Alright, so another transformation would be a shift. So if we were to just add or subtract some particular real number, let's say k, to the a to the x function, well, this is going to be the result of shifting a to the x. Because it's just a constant added or subtracted at the end, this is going to be a vertical shift. And because it's minus k, it's going to be down k units. K many units. Alright, so if this is a graph of a to the x, this is a graph we started with. We've got this horizontal asymptote at 0. Then shifting it down k units is going to bring you down to k, or negative k, I suppose, down here. And your asymptote will shift down here. Okay, so now your graph will look like this. To give you a more concrete example, let's use black here. If I wanted to graph the function, let's call it g of x is 3 to the x plus 2. Alright, I'm going to start by drawing the general graph of 3 to the x. The shape is the same as all the other ones we've drawn because our base is greater than 1. And now I'm going to shift that up 2 units. So I need to shift everything up 2 units. So my y-intercept was at 1 before, now I have to shift it up 2 units to 2. Oops, sorry, to 3. Because 1 plus 2 is 3. Alright. And my horizontal asymptote had been at 0, but now that also is going to shift up 2 units. And now I'm going to have a horizontal asymptote at 2. So your graph is going to look roughly like this. Okay. Let's look at another type of a translation. This time, let's look at the graph of a to the x minus h. Now this time we've replaced x with x minus h. So remember, replacing x with x minus h results in a horizontal shift, and it does sort of the opposite direction as you might think. So x minus h is actually going to shift the graph to the right. So this is shifting the function a to the x to the right h many units. This is a horizontal shift h units to the right. So if your general graph a to the x looks like this, shifting it h units to the right is going to look like, instead of a point at 0, 1, I'll have a point at h, 1. It's still going to be approaching 0, so your vertical asymptote hasn't changed because you haven't shifted vertically at all. Oh, I'm sorry, your horizontal asymptote hasn't changed because you haven't shifted vertically at all. You've just moved your point from 0, 1 to h1. Again, let's do a concrete example to make sure we understand how this works. let's say I wanted to graph the function g of x is 5 raised to the x minus 6. I'm going to start with the function 5 to the x. It has the same general shape as all the other ones that we've seen. It has a y-intercept here at 1 and a horizontal asymptote at 0 as x goes to negative infinity. So replacing x with x minus 6 is going to shift this entire graph 6 units to the right. So instead of having a point at 0, 1, I'll have a point way over here at 6, 1. But my horizontal asymptote will still be at 0. Okay? And if it had been a 6 plus x, or x plus 6, I would have shifted it to the left instead. Alright, so this tells us how to do vertical shifts, horizontal shifts, and reflections over the y-axis. Our last one would be a reflection over the x-axis. So if we were to replace a to the x with negative a to the x, this is going to reflect f of x over the x-axis. So again, if this is a to the x, has a y-intercept at 1, then reflecting it over the x-axis is going to give you a graph that looks like this. Now it's going to have a y-intercept of negative 1, but the horizontal asymptote is the same. To give you a concrete example, let's say I wanted to graph the function f of x is equal to negative 7 to the x power. Start off by graphing just regular 7 to the x power that has the same basic shape as all of our other exponential functions. Now negative 7 to the x power is just going to flip it over the x-axis. So it's going to look like this. Okay, now let's try to put that all together to graph something a little bit larger. So let's say we wanted to graph the function negative 3 to the x minus 2 plus 4. So I'm going to do this in stages. First I'm just going to graph, I'm just going to call these functions y for now. So first I'm going to graph 3 to the x, then I'm going to graph 3 to the x minus 2, then I'm going to graph negative 3 to the x minus 2, and finally I'll graph that f of x function that I want, negative 3 to the x minus 2 plus 4. Alright, start with 3 to the x, same basic shape as all of our other exponential functions. The y-intercept of 1. Now graph 3 to the x minus 2. Remember, this is going to represent a horizontal shift 2 units to the right. When you replace x with x minus something, you move that many units to the right. Okay, so I'm going to need to move 2 units to the right, so now I'll have a point here at 2, 1 instead of 0, 1. But I still have the same horizontal asymptote as x goes to negative infinity at y equals 0. So this is at 2, 1. Alright, what's next? Next we're going to take that whole function, 3 to the x minus 2, and make it negative. When you take the whole function and make it negative, this is going to reflect the last graph across the x-axis. So my point at 2, 1 is now going to become a point at 2, negative 1, because I flipped it over the x-axis. Right? The rest of the graph gets flipped as well. So now you're looking at something that looks sort of like this. And finally, we're going to take the graph we just drew, and we're going to vertically shift it 4 units. Shift 4 units up vertically. And so my point at 2, negative 1 is going to move up 4 spots. So up to 0, then 1, 2, 3. So now I have a point at 2, 3. Okay? And so the rest of the graph is going to have that same basic shape. Now where's my asymptote going to be? The asymptote originally was at y equals 0, but I've shifted it up 4 units. So it's going to move from 0 up to 1, 2, 3, 4. So let's draw in this asymptote at 4. Okay, so we see how putting together these various transformations works similarly to how we did it with different types of polynomial functions in the last unit. Now, the most important exponential function that you're going to see, especially in calculus, is the exponential function e to the x, so the natural base e. Now we'll say for now that the natural base e, or the number e, is just roughly 2.718. It's a little bit more nuanced than that. This seems pretty arbitrary, but it's a really important number, and you'll see why it's important when we get to calculus. It's hard for me to justify it now without the tools of calculus to explain why it's an important real number. But it is an important real number, and it's irrational, which means its decimal is never going to repeat itself. It's just going to keep on going forever without ever repeating. So this number e, of course, it's bigger than 1, so we know what the rough shape of the function is going to be. It's going to look something like all the other ones we drew. It's got a y-intercept of 1, grows very quickly in the first quadrant, and it has a horizontal asymptote at 0. We can see from the picture that the domain is all real numbers. And you can plug anything you want into this function, f of x equals e to the x. Right, any real number that you plug in, it's going to be something, right? It's going to be some number. The range, though, the outputs of the function are all going to be positive. Because we have this horizontal asymptote at 0, the function's never going to cross the x-axis, you're never going to get an output of 0, and you're never going to get any negative outputs either. So we can say that the range is just 0 to infinity with open brackets because we're not including 0. The end behavior just means, does it have a horizontal asymptote? And yes, it does on the one hand. As x approaches negative infinity, we get a horizontal asymptote at y equals 0. That is, f of x approaches 0. But as x goes to positive infinity, there's no asymptote here. The outputs of the function are also going to be heading towards positive infinity. Okay, we can see that happening on the graph. Now the last thing it asks about is the inverse. Does this have an inverse function? And looking at the graph, it should have an inverse function. Remember, it needs to pass the vertical line test to be a function and the horizontal line test to be a one-to-one function. It passes both, which means there should be an inverse function. And remember, we said at the beginning of the video that in a sense you can try and figure out what it would be by reflecting this function over the line y equals x. So you're going to end up with a function that looks something like this. It's going to have an x-intercept at 1, it's going to have a vertical asymptote at 0, and it's going to grow very slowly. So what is that function? Well, that's what we'll figure out in the next video.